Hello, this is Greg McMurphy. I'm starting out. This is video one in a series of videos talking about vector addition and how to organize our work using a tool that we've come up with. It's called the vector addition machine or the vector addition calculator. This is what I'm going to use as an example for our work today is Lesson 8, questions 20 and 22. They give us a couple of vectors to look at. We'll break them down and add them together. Vectors, by definition, have a magnitude and a direction. And in our electrical analysis, the direction is defined as an angular displacement in degrees from our reference, 0-degree reference. We can be displaced only up to, our displacement will be no greater than 90 degrees. So we're in quadrant 1 and quadrant 4 of the Cartesian plane if you're interested in that factoid. What is the reference? Well, in a series circuit, current's the same everywhere. And we're going to use our mnemonic device of Eli the Iceman, and we'll know that all of our inductive vectors in a series circuit will be positive angles, and our capacitive displacements will be defined as a negative angle. Of course, you can use, let's say if this is negative 30-degree displacement on a capacitive RC circuit, you could also call it positive 330, but let's just keep it simple, use the included angle. But just remember that it's a negative angle. In a parallel circuit, the one thing that's the same everywhere is voltage. So using the same mnemonic, Eli the Iceman, we can see that the capacitive current vectors or power will be positive angles, and then the inductive will be negative angles. And we need to be able to do that, keep track of the positive and negative, especially once we move into a little more complex circuit where you have combination circuits where things are both in series and parallel. Why don't we take a look at this tool I'm talking about. Here, all it is a grid system designed to keep track of all the components of a vector and then give a nice clean set of columns to add up the verticals, nice clean set of columns to add up the horizontals, and then calculating out the resultant vector using trigonometry facts, using Pythagorean and the tangent. So let's run through an example. Take a look at question 20, lesson 8. Question 20, lesson 8 gives us a vector that's defined as having 55 vertical and 75 horizontal. 55 vertical, 75 horizontal. So how do we find the length of this vector, the v sub r? Pythagorean theorem, knowing the opposite and the adjacent, the vertical and the horizontal, use Pythagorean theorem. That should look familiar. That's how we're calculating voltage drops in a series RL circuit, is how we're adding currents in parallel when you have RC or RL. Any vectors that are 90 degrees out of phase with each other. We're going to go, our go-to formula is Pythagorean. So if you run 55 squared, 75 squared, take the square root, you should come up with something about 93 units, whatever that is. Ohms if it's in series, amps if it's in parallel, volt amps if it was power. How about the angle of displacement from the reference? If you run, here's your formula. Do the arctangent of the ratio you know to find the angle. It's as if you're calculating this ratio, writing it down as a 4 or 5 digit decimal number, then go to your paper trig table, run your finger down the tangent column until you see an approximation of that calculated value, and then running your finger over to find the angle associated with the ratio you calculated. Thankfully, our calculator does a much quicker and much more accurate job of that than we can do with a paper trig table. If you run these values through your calculator, you should find 36.25 degrees. And remember, you can always hit pause on these videos and catch up, run your calculations before you see me write the answer. The next vector, so let's see, this one was 93 with a phase angle of about 36. The next one on page 66, question 22, they give us a 100-unit long vector which has a 35-degree displacement. All right, so they're giving us the length and the direction. So to use the table that way, knowing the length of the vector and knowing the angle, you can calculate the opposite, right? The SOHCAHTOA, come up with some mnemonic aid for your trig functions. And you can see that your opposite, if you're looking for the opposite, you multiply the hypotenuse times the sine of the phase angle. Take the length of the hypotenuse, or the vector length, times the sine of the phase angle. Do it in that order. Get used to, drill it into your brain, get habituated to putting the vector first, then the sine of the angle. You'll find you'll have much less problem with the calculators we use in class, because if you do it in the opposite direction and forget to close your parentheses after plugging in the angle value, you'll end up with a very odd answer most of the time. So the vertical component associated with that is 57.36. The horizontal component, using cosine, right? The horizontal component is adjacent to the angle. Multiply hypotenuse times a cosine, you'll get adjacent. Should come up with about 81.92. So, adding these two vectors together is as simple as adding the two, the horizontal of the first plus the horizontal of the second, get a value, add the vertical of the first to the vertical of the second. You'll get a total vertical, total horizontal. Run yourself a little Pythagorean and you'll calculate out this hypotenuse. That's your resultant vector. That's the head to tail method of addition, from the tail of the first to the head of the last. That's your resultant vector, magnitude and direction. So add them up. Let's add up those columns. The vertical column, I'll keep that green. I can carry that 0.36 down. 7.5 looks like about 12. 5.5, that's 112.36 vertical. Horizontal is 75. And 81. 75 and 81. Confused myself with my little notation about the angle up there, so forgive me as I get lost. 75 and 81. I'll carry down my decimal right here. 1 5 is 6. 8 and 7 is about 15. 156.92. So to find the resultant vector, we're going to do Pythagorean. to take the square root of 156.92 squared plus 112.36 squared, and we'll come up with about 192.999. Maybe 193 would be close enough for you and me. Or 92.99. So you can see that being 1 degree off, 1 1/4 degree off, is almost equal to a straight line addition. And then the angle, this new phase angle, if we're looking at the not quite to scale model diagram I made, it should be apparent that it's not going to be 36, but it's ought to be more than 35. So we should have a phase angle between 36.25 and 35. Why don't we run a quick second tangent? That's our arctangent of the opposite, which is 112.36 divided by 156.92, and we come up with about 35.6. Gosh, it's right what we expected. Right in the neighborhood. Drawing yourself a halfway decent scale drawing will help you anticipate what your value should be. And if you do a really good job, of course, you can actually add vectors by doing good scale drawings. One last little tidbit: if we're going to be adding, say, something that's, let's say this is a parallel current that's RC, it's more resistive than capacitive, but that's a current that's a capacitive current, and we're going to add a vector that has a negative phase displacement. You really have to keep track of that negative angle, this negative angle. As long as you do that, you will come up with a negative vertical number. So if you have a negative, say a negative 20 degree phase angle, you'll have a negative vertical. And as long as you keep track of your sign on that, you can see you're adding a positive number, subtracting this vertical, and you'll come up with a net amount of vertical action going on down here at the bottom. You'll end up with, in this case, a little bit of positive, whatever the net is will be positive. That, I think, will be the end of this video. Hope it helps. If you move on, the next video goes through a combination circuit where we have a capacitor in parallel with a series LR component. Take care, give us a call if you have any questions.